Question 8, 8.1 says we have to determine f prime of x from first principles if f of x is equal to 1 over x. Okay, so something you can actually do first before deriving it is you can use the actual rule of derivative to derive this function first, and just to make sure that you have the right answer, so that when you derive using first principles, when you get your answer, you can compare it to that. So we have f of x is equal to 1 over x. Okay, what we can do is prepare this to be derived. So f of x is equal to, the problem now is x is on the denominator. It shouldn't be on the denominator, it should be on the numerator so that you can properly derive it. So when you move it to the numerator, there's a consequence for this. It means that your exponent, which originally was 1, right, it's going to become negative. So it's now negative 1. And then now it's ready to be derived. So you can say f prime of x is equal to 1 times negative 1 is negative 1. And then x to the power of negative 1, subtract 1 from that. So you have x to the power of negative 2. Then if you put this in a way that its exponent is positive, this is just going to be negative 1. Since this is on the numerator and the exponent is negative, you bring it to the denominator, which makes the exponent positive. So we already know what the answer is now. And let's just go ahead and derive this using first principles, okay? From first principles to see whether we're actually going to get to that answer. So let's go ahead. When you are deriving from first principles, you're going to use this formula. So this is really the formula for the gradient of a function. We have f of x and we have f of x plus h. So we have to first find f of x plus h. So I'm going to go ahead and find that and say f of x plus h is equal to, meaning wherever I see x in my function of f of x, I'm just going to replace it with x plus h. So I have 1 over I see x. I'm just going to say plus h. Okay, so really just adding an h to the x. So now we know what that is, and we can go ahead and use our formula. So we're deriving, we're going to go ahead and say that this is equal to, and we're saying the limit as h approaches 0. You'll keep saying this until you get to the substitution. So this is f of x plus h. So we put 1 over x plus h. And then minus f of x, right, which is 1 over x that we have there. And all of this is being divided by h. Now, this looks quite complicated, and you don't have to write it like that. What you can do is the numerator, write that as one term, right? So I'm going to leave that as 1 over x plus h minus 1 over x. And then I'm dividing by h, so divided by h. Since these are fractions and this is not a fraction, we can make it a fraction by putting it over 1. Okay, so that's what we have. And then this is equal to, we're still going to have the limit as h approaches 0. And now we have to work on this fraction. So do you see that you're subtracting in a fraction? When adding or subtracting in fractions, you need to make sure that the denominators are the same. So how would we make the denominators the same? If you look at these fractions separately, the only way to make the denominators the same is to really multiply them by each other's denominator. So this one you'd multiply by x, and so what you do on the bottom, you must do on the top. This one, you would multiply by that x plus h. So times x plus h and times x plus h, right? But of course, as like that. So that's actually what's going on there, because you can't multiply this one by h. It's not going to work. If you multiply it by h, and I've seen students say multiply it by h because they see a plus h here. The thing is that's going to become an xh. So that's not the same thing as x plus h. So that's what we do there. And so our common denominator is going to be, as you can see, since this is two terms being multiplied by one term, you have to write it as x times x plus h. That's your common denominator. And the numerator that we will have, let's just be very careful here. 1 times x is just x. That's fine. But please note that we have a minus here. So if we have a minus first, and then we have this, you see, it's the 1 times the x plus h. Since we are multiplying by something that has two terms, we still have, if you look at it as if the 1 is still there, it's really like 1 times x plus h. You see that now that negative is going to affect what you have in your brackets. Okay, so that's kind of what's going on there. Then we have divided by, and we have, instead of making this division, we can use, since we are dividing by a fraction, we can use the rule called tip and times, meaning you tip the fraction, you swap the numerator and denominator, and you change the division sign to a multiplication. So this is what we have, and then we can say is equal to the limit as h tends towards 0, and we can simplify that. That is going to be x. When you distribute, you get negative x and negative h over, we still have here x times x plus h, and then this is being multiplied by 1 over h. Okay, so now that we have this, you can see that the x and the x would simplify to 0. So there on the numerator, I still write this because I've not substituted yet. So negative h over, and you have x times x plus h multiplied by 1 over h. So when multiplying fractions, you can cancel common factors if they are in a top-down position. So like there's a common factor on top and the bottom. But you can also cancel common factors diagonally. So do you see there's an h there and an h there? So that cancels. It's like h divided by h is 1. So there's a placeholder of 1. And h divided by h there, we'll still have our placeholder. So this is equal to the limit as h tends towards 0. And we're going to say negative 1 times that 1 that is still there, which is negative 1, over, and here it is this times the placeholder of 1 remaining, which stays the same. Okay, then we are now ready to substitute. We've gotten the function to a point where if you substitute h, it's not going to make it undefined. You see, if you had substituted h here, your denominator would have been 0, and so this would be undefined. So that's the whole purpose of simplifying. Okay, so now we can finally substitute. So we're just saying that f prime of x is finally equal to, say, negative 1 over, in place of h, you're going to put 0, so x times x plus 0. And f prime of x is equal to, we have negative 1 over, now you see x plus 0 is equal to x. So x times x is x squared. And you see we get the answer that we got when we use the rule. So use the rule just to check and make sure that your answer is correct. Okay, so that is 8.1, and we move on to 8.2. Okay, so we're finally on 8.2, and 8.2 says we have to determine the derivative of this function. So d over dx. So with this, I'll just say, just pay careful attention to notation. You will notice that these ones that have this, some sort of derivative instruction, and then you have your brackets. The thing about them is you first have to prepare your function to be derived, or your expression to be derived. After preparing it, then you go ahead and derive it. So just take note of how we're going to write this. An alternative to writing it this way, you could have also written it like, they could have also written it like that, and then, you know, put the function in. So you would do the same thing that we're going to do here in this situation. Okay, so what we do here is we're going to go ahead and say, because we're not deriving yet, we'll keep writing d over dx. And then let's go ahead and simplify what we have here. So the ground rules are, where you have an x, it should not be a surd. Okay, anything that is a surd and an x, you need to kind of change it. But if you have a number that is a surd, it's fine, because that number is just a number. Okay, so you don't have to change numbers that are surds, but you have to change variables that are surds. So let's go ahead. We see here, this has to be changed. Since it's being square rooted, we can square root it. The square root of 4 is 2. And the square root of x to the power of 6 is x to the power of 3. Because what's actually happening is you have the square root of x to the power of 6. This root has an invisible 2 here. You keep the base the same, and you say the inside exponent divided by the outside exponent. And that's how we get that. So that's what we have there. And this is now fine. See, we have x to the power of 3. That is perfect and ready to be derived. Then here, is there anything that you need to change there? No, there's nothing you need to change there, because your square root is on its own. The x is not under the radical, so you can leave it like that. It's just plus the square root of 2, and we have x to the power of 2. Okay, so that's what we have there. Now we are ready to derive, and because we are deriving, I say is equal to, and I go ahead and start deriving. So coefficient times exponent, that gives you 6, and we have x to the power of, subtract the 1 from the exponent, gives you 2. Then here, coefficient, the square root of 2 times exponent, gives you positive 2 square root 2. Then x squared minus 1, gives you 1, which we don't have to write, and that is our answer. Okay, so that is our answer there. Moving on to the next question. The next one is another derivative question. We have 8.2.2. We need to determine g prime of x if g of x is equal to this. So let's look at this. Do you see that there is a denominator of x squared? We shouldn't have that. Now, I know normally you would think, okay, maybe we need to move this to the top. That wouldn't work in this case, because I want you to see what's actually going on here. Do you see that you have 3 separate terms and all of them are being divided by x squared? We can actually expand that. So how they came about to be like this is because they were probably written like this before. So it was g of x is equal to 3x to the power of 4 over x squared. Okay, so each of them would have had this common denominator of x squared. That's why when you added them together, they looked like that. And then you'd have had minus 4x squared over x squared, and then plus 6 over x squared. That's why when they added them together and subtracted, of course, when you did that, it became that. And now you can simplify them individually. So we have g of x is equal to, if you divide this by that, you get 3x to the power of 2, and then still have minus there, divide that, you get 4, and then x squared will cancel. And then here, you just have plus 6 and then x squared. But what we can do to get this to be derived is your x should not be on the denominator. So let's move it to the numerator. And so that makes the exponent negative. Now we can derive. We can say g prime of x. So we have 3 times 2, which is 6. And then we have x. And then we subtract 1 from that is 1. You don't have to write that. Then you have minus 4, of course. So when you are deriving a constant, it becomes 0. Okay, the gradient of every constant, like if you have y is equal to negative 4, it's a straight line. If you derive this function, it gives you 0, because every straight line or vertical flat line has a gradient of 0. That's the reason why. Okay, so we have that, and then this, when you derive, it's going to be this positive 6 times the negative 2, which is negative 12. We have x to the power of negative 2 minus 1, which is negative 3. Okay, so I'll just check. It's only 3 marks. So they would have given you a mark for separating, but not really expanding it. They don't give you a mark for doing this. It's the actual act of separating. So a mark for separating, probably a mark for putting that in its correct order, that, and then deriving. So it's 3 marks. You don't necessarily have to put this or write this as a positive exponent. You can if you want to, but at this point, it's fine. Okay, so that is that. Moving on to the next question. Then we have the last question of question 8, and it says the equation of the tangent to f of x is equal to 3x squared plus bx plus c at x is equal to 1 is given by y is equal to that. So the equation of a tangent to this parabola, okay, at x is equal to 1 is given by this equation. You have to determine the values of b and c. Okay, let's go ahead and visualize what's going on. So they say the equation of a tangent to f of x, which we can see is a parabola that is concave up because the a value is greater than 0. So we have a concave up parabola, and we have a tangent to this parabola at x is equal to 1, right? And this is the equation of the tangent. I want you to also notice that the equation of this tangent, do you see that? Your gradient is greater than 0. So it is an increasing function. So it's going to look something like, I have the tangent there. I'll just pull that closer, of course. So you have that, and then it's touching the graph once. And we know it's touching the graph. So we know the equation of this tangent. It's y is equal to 9x minus 9. We also know where it touches the parabola. It touches the parabola at the point where x is equal to 1. So as you can see, because it's on this line, we can even find the y value. And then they also told us the equation of the parabola. Okay, so we have the a value at least. So they want us to find b and c. Okay, you see, this has to do with equations and simultaneous equations, really. If you have to find 2 variables, you will need 2 equations. So we're going to have to see how we can form these 2 equations. So since this is the equation of this function, in order to form this, I can see a way of, first of all, it would be helpful to find the y value of this. Okay, I can see a way that we can use the information that we have been given twice to form two separate equations. But I'm going to go ahead and find well, it's not really necessary. Let me show you. So you see, the powerful thing they gave you here is telling you that this was a tangent to this parabola. I want you to understand that the parabola, at different points, it has different gradients. So different gradients here, right? But the thing about a tangent is that a tangent is a straight line. And so its gradient is constant, okay? It doesn't change like a parabola. So because its gradient is constant, we already know the gradient of the tangent, it's 9. So because they meet, right, the tangent and the parabola, they meet at the point where x is equal to 1. Let me get rid of this. We don't really need this now. So because they meet at the point where x is equal to 1, we know that at this point, their gradient is exactly the same. So here's the first equation we can form from that. Knowing that their gradients are exactly the same, what I would do is I would attempt to find the gradient of f, because that's what I'm saying. I'm saying the gradient on f and the gradient of the tangent are the same at this point. So find the gradient of f. It's f prime of x is equal to, we say 3 times 2, which gives us 6. We have x, you subtract 1 from your 2, you get a 1, and you don't have to write that. It's invisible. Then you have here plus b. You see there's an exponent of 1 on the x, so you say b times 1, which is going to give you your b plus b. And then when you have your x, you see it has an exponent of 1. When you subtract that 1 from it, it becomes 0. Anything to the power of 0 gives you 1, and the b times 1 will just give you b. So this is what you get when you derive, when you try to find the gradient of the parabola. Now, we're not just looking for any gradient on this parabola. We're looking for a specific gradient. We're looking specifically for the gradient at this point. And we know that the gradient at this point is 9, because that's the gradient of your tangent. The tangent and the parabola have the gradient, the same gradient at that point. So what we're going to do is, before actually substituting the gradient, I'm going to say I'm specifically looking for the gradient of f at a particular point where x is equal to 1. That's what I'm looking for. So I'm going to substitute 1 into that. So substitute 1 plus b, you really just get 6 plus b, right? That's f prime of 1. Now the thing is, we already know what the gradient is at this point. That gradient is 9. So I'm going to substitute it into the gradient. F prime of 1 is speaking about your gradient of f at the point where x is equal to 1. I know that gradient is 9. So I'll rewrite that, and it's equal to 6 plus b. As you can see, we're already going to solve for b. Take 6 over, that gives you 9 minus 6, gives you b. And so you know that b is equal to 3. There we found our first expression. So our first equation technically. Now, what can we use to find the second equation? Well, it's quite simple. All you have to do is, why don't you just find the y value of this point? Once you find the y value of this point, substitute the x and y value into your graph of f, since this point lies on the graph of f, and then you'll find c, because you already have b. Okay, so that's the second thing we can do. So let's go ahead and find the y value. We can find the y value because it lies on this graph. So we say y is equal to 9, and then substitute in place of 9, 1, then minus 9. So y is equal to, that's 9 minus 9, which is 0. Okay, so that's the point. The point of contact, okay, with the tangent and that graph is 1 and 0. Now we're going to substitute this into our equation of f. So the y value is 0. I say 0 is equal to, and the x value is 1. So 3 times 1 squared plus, and we know what b is, it's 3. So 3 times 1 plus c. That's what we're looking for. And now we can go ahead and find this. So this is equal to, we have 0 is equal to 3 times 1 squared is just 3 plus 3, which is 6, plus c. Take 6 over, negative 6 is equal to c. So there you have c and you have b, and that's actually what they asked you to find. So that is that question, and that is the end of question 8. And then we move on to question 9. Okay, so now we're on question 9, and question 9 says, the graph of f of x is equal to ax cubed plus bx squared plus cx minus 5 is drawn below. And then we have e, which is negative 1 and 0, and g, which is 5 and 0. And these are the x-intercepts of f. The first question is to find the values of A, B, and C. Now, I know many grade 12s actually struggle with when they give these questions, where they want you to find the formula of your cubic function. The thing is, you just have to focus on one thing. Focus on the graph and what they gave you. So you look at the graph, and do you see that the only points that they are specifically giving you are x-intercepts? So it means we're going to use the x-intercept formula. But now you have to use the proper formula. You see, with the x-intercept formula of a cubic function, and remember, because this is a memo, it's also a teaching opportunity, so I will explain in more detail. The thing about it is, let's just briefly explain that. You can have an x-intercept formula where you have 3 roots, like that, right? 3 roots, 3 x-intercepts. So with this type of formula, it's going to just look like this. Y is equal to A times x minus x1, meaning root 1, times x minus root 2, times x minus root 3, because these are 3 separate roots. Then you have an x-intercept formula where your graph somewhat does this. Doesn't always have to look like that. It can also look like this, for example. But ultimately what's actually happening is you have roots, but you have 2 roots instead. And the thing about these 2 roots is that one is a turning point and a root at the same time. So this will be the formula for that. Y is equal to A times x minus x1 times x minus x2 squared. So the one that is squared, you can already guess, would be the one that is a turning point and an x-intercept at the same time. Okay, so they gave us x-intercepts. We're going to use one of the x-intercept formulas. And of course, we're going to use this formula. Okay, so let's just establish what is our x1 and x2. Our x2 must be the one that is a turning point and an x-intercept. So x1 and x2. Our x1 would be this one, because it's just an x-intercept, that's all, 5. And now x2 is the one that is a turning point and an x-intercept. So let's go ahead and substitute this. So we're going to say y is equal to, we have A times x minus our x1 is the 5. And then times x minus our x2 is the -1, which is really minus -1, which just becomes a +1. You just say +1 all squared. And now you see that the only thing missing in your formula is just your A. So to find A, if you could fill in numbers for x and y, because that's also x, then you would have A. So it means that you need a point, because a point is the only thing that will have x and y like that. So let's look and see, did they give us a point? Well, the graph looks empty, but if you look at the formula they gave you, do you see that they gave you a y-intercept? The only thing without x, your constant, is your y-intercept, and that's -5. So that's a point. So it means on your y-axis, this graph intersects the y-axis at -5. So the coordinates of that would be 0 as your x value and -5 as your y value. That's what we're going to substitute into this equation. So we're going to go ahead and substitute 0 and -5 in place of x and y. So that makes that -5 is equal to A times, and in place of x, 0 minus 5, and then 0 plus 1, all squared. Let's simplify. We have -5 is equal to, we have A. Let me actually just simplify on screen. 0 minus 5 is -5. 0 plus 1 is 1. 1 squared is 1. So you have -5 times 1, which is -5. And so to solve for A, you would divide both sides by that -5, and you see that A is finally equal to 1. Now that you have A, you can take A and substitute it into the part of the equation that was almost complete. So we're going to substitute it there. So that is, but I'm going to call this f of x because it is f of x. F of x is equal to, in place of A, we say 1 times x minus 5 times x plus 1 squared. Now, 1 times anything stays the same. So I can actually just pretend that 1 is not there. It multiplied. So f of x is equal to, we're going to leave this x minus 5 and then distribute that. Remember, that can be expressed as x plus 1 times x plus 1. That's what that squared is. So you could distribute the traditional way, or you could just do this. you look at the first term, you square that. That's x squared. Then you say first term times second term gives us x, and you multiply that by 2. So you get positive 2x. Then lastly, take the last term and square it, which will give you positive 1. And now we can distribute. So f of x is equal to, you say x times x squared, which gives you x cubed, x multiplied by 2x, which gives you positive 2x squared, x multiplied by positive 1 gives you positive x. Negative 5 times x squared is negative 5x squared. Negative 5 times positive 2x is negative 10x. And then negative 5 times positive 1 is negative 5. You see, end up with the same constant. So we have f of x is equal to x cubed is the only thing with the cube. Then we have positive 2x squared minus 5x squared, which gives you negative 3x squared. And then positive x minus 10x gives you negative 9x. And we have minus 5. So because they told us that f of x was equal to the ax cubed plus bx squared plus cx minus 5, it therefore means that a is 1. As you can see, the coefficient is 1. We already found a. B is negative 3. And C is negative 9, just as they have said it is. Okay, so the key thing here, I know many students struggle with this. The key thing is look at your graph, look at what they gave you. Based on that, you're going to use a particular formula. So that's 9.1, and we finally move on to the next question. The next question, 9.2, says, calculate the value of x for which f has a local minimum value. Okay, so you have to think about the way f looks. F is that kind of graph. It's a cubic function with a positive a value. So that's what we have there. The local minimum, okay, would just be the lowest turning point. So that's your local minimum. So you see what they're actually asking you for. Calculate the value of x for which f has a local minimum. You just have to find the x value of your local minimum, okay, of that turning point. So let's go ahead and do that. We're going to have to try to find the turning point first. That's what we're going to do. So take the function of f, which we now know, just rewrite it. And now that we have our function of x, we're going to find the turning point since we're looking for the local minimum. So we're going to derive this function, f prime of x is equal to, and so that's going to give you 3x squared and minus 6x and minus 9. And now that you have that, to find the local minimum, you're going to make the gradient equal to 0, because the logic behind that is that when you have turning points, you see, it's all about gradients. We're looking at that. Here, the gradient is positive because this part of the graph is increasing. Then the gradient stands still. The gradient is 0 at this point. It's stationary. That's why these are stationary points. Then the gradient starts to get lower. It starts becoming negative, right? So these gradients are negative because this part of the graphs, they're really just decreasing. Then it reaches a point where it stands still and then goes up, okay? So at the stationary point, your gradient is stationary. It's 0. So we're going to say 0 is equal to 3x squared minus 6x minus 9. Okay, so just a bit of algebra here. Just going to go ahead and divide both sides by 3 since it's common all through. So we have 0 is equal to x squared minus 2x minus 3. Okay, so let's go ahead and factorize that. 0 is equal to, open up two brackets, we have x times x. And then factors of negative 3, they can give you 2. Why don't you just try negative 3 plus 1? That gives you negative 2, and if you multiply, it gives you negative 3. So x is therefore equal to 3, or x is equal to negative 1. So how do we know which one is our local minimum? Well, we know our graph looks like this. So the minimum is this one. As you can see, this would be an x value that is bigger than, let's just call that b. It's going to be an x value that is bigger than the x value here. So you know that you're supposed to take the bigger one. So just take, you know that it's going to be 3. So I'll cancel the negative one. Just in this scenario, I'm canceling it. And I'm saying that the x value for where we have a local minimum is where x is equal to 3. And that is our answer. Moving on to the next question. Question 9.3 says, use the graph to determine the values of x for which f double prime of x multiplied by f of x is greater than 0. So let's go ahead and get the graphs first. So if this is our graph, and they're specifically speaking about f of x, which is the one we have, and f double prime of x, let us just go ahead and find out what this one is going to look like. So in order to get to that, this is what happens. When you have your cubic function and you derive your cubic function, you end up with a parabola. Because this cubic function's a value was 1, meaning it's a value greater than 0, you have a cubic function that kind of looks like a capital letter N, okay? It's just more curved. If it's negative, it will look like a backwards N, okay? Just more curved. So because we have that, and because a was positive here, when you derive it and get a parabola, your parabola will also be concave up. But I want you to see how the parabola would look. It looks like that. But what actually happens is you see, I didn't draw it so well. Let me actually just try to put it right, like here, right? What happens is the x-intercept of these parabola would have the same x value as the turning point of your cubic function. So that turning point here, it would be the same x-intercept. That's why I said I didn't draw this so well. So I think it should be fine like that. So that same one should be that. But please notice that this parabola is when you derive f. So this is f prime. So what does f double prime look like? If you derive a parabola, you get a straight line. Because your parabola was concave up, your straight line is going to be an increasing function. But we need to at least know where it's going to be. So the thing about this parabola is the turning point of your parabola, the x value of that turning point is going to be the same x value as your point of inflection of your cubic function. Okay, that point of inflection. Now here's the thing about the point of inflection, that x value of the point of inflection, so they're just speaking about the x values, is going to be the x value of your x-intercept of your straight line. This is f double prime of x. Okay, that's what it looks like. And that's how you know what it looks like. So you can kind of already look at the function and start drawing it in your head, and you can kind of see what it looks like. But of course, they expect you to, sketch it with a pencil so that you can find out what to do. So I only did that so that you know where this comes from. Okay, that we know how to get that now. That's the x value of the point of inflection of your cubic function. So I'm going to erase the parabola one because we don't really need that. Okay, I think this part is necessary. And now we can think about what we need to do. So because they say f double prime of x multiplied by f of x must be greater than 0. So the straight line times the cubic must be greater than 0. On your graph, the only way you can find this is, please note that when they say f double prime of x, they're referring to the y values of that graph and the y values of this graph. When you multiply them, they must give you something positive. The only way that's possible, okay, if you multiply two things and get a positive number, is if the two things are both positive or they're both negative. That's the only way that that's possible. So in other words, what you're looking for in these graphs is you're looking for places where the graph has negative values, both negative values or both positive values. And we can go ahead and search. Remember, you can use your trusty vertical line. Okay, hold on to your vertical line and let's look. So when we start off here, we know that of course this graph continues going down like that. And so it has a negative value, right? And at the same time, the cubic function as well. Let me actually just start from here. So it has a negative value. The cubic function also has a negative value. They're both negative here. That's one of the scenarios. Let's see. They keep being both negative. See that point? If that's a coordinate, that has a negative y value. This one also a negative y value. Okay, keep going. They both still have negative. And then here, something changes here. The reason I say something changes here is because think about the cubic function. What is the y value this cubic function has here? It's 0. Okay, so not negative, 0. And here, this one has a negative. So we'll keep that in mind. So it does not happen where x is equal to -1. We keep going. See that point over there has a negative y value. The y value of the straight line, negative y value. Keeps happening, keeps going, still negative, both negative. And then you get to here. At this point, the straight line has a y value of 0, right? And this has a negative y value. And now after that, look what happens. The straight line has a positive y value and the cubic function has a negative. We don't want that. We want them to both be both negative or both positive. So let's pause and actually just take the ones that we just found so long. So long, we found that we have both negative y values here. So here on that graph, and for this same x value, it's going to be, it's going to be for this part. But you need to remember not to include -1, because at -1, that y value is 0. If you take a y value of 0 and multiply it by the y value of negative whatever that is, you get 0 and not a positive number. Okay, that's not what they asked for. So we can see that it's working all the way here. So what are the x values for which it's working for? All these values, all of their x values are values that lie here. These are values that are less than -1. So I'm going to say that. I'm going to tell them that x is, well, I'm going to need to change that a little bit. The reason why I'm saying so is because you see that if we keep going, it also worked here. It stopped working like here, right? It also worked here because they both have negative y values here. See, for here and here, they both have negative y values. So I'm going to find a way to sum this up. What we can actually say is we need to find that x value first because we don't know what that is. We can see that it's working for values that are less than this, but of course not equal to -1. So let's go ahead and find that point of inflection, the x value. We only have to find the x value. So why don't we just use the derived function that we already have and then derive that further? Then we will find the point of inflection, the x value of the point of inflection of our cubic function. So when we derive this, we get f double prime of x is equal to, that gives you 6x minus 6. Then make that equal to 0 to find the point of inflection. You have 6x minus 6. Just take your -6 over, equal to 6x, divide both sides by 6, and therefore x is equal to 1. So we know our point of inflection now. And so now that we know that, we can answer them. See the highlighted parts, that's all the places that it's working. We're going to say that x is less than 1, but x is not equal to -1 because at -1, that doesn't work out, okay? That has a y value of 0, that has a negative y value. When you multiply them, they don't give you something positive, they give you 0. So there we say x is less than 1, but x is not equal to -1. We got that part. Let's keep seeing places that it's also going to work. So let's take our vertical line, and so you would use a ruler, of course. Take our vertical line and keep looking. So here we saw it didn't work because that has a y value of 0, that has a negative y value. Keep moving. This has a positive y value, that has a negative y value. That's not going to work. Positive times negative is negative, not positive. We're looking for where it's going to be positive. Keep going. So positive and negative, and it keeps doing that until you get to 5. At 5, the cubic function has a y value of 0. And at 5, the straight line has a positive y value because it keeps shooting up, right? And so after 5, do you see that the cubic function has a positive y value? And at the same time, for the same x value, this straight line will also have a positive y value. So positive times positive is a positive number. That's actually working out. So we can see that it starts to work from here onwards as well. Here. And of course, if that graph continued going, like after 5, it shoots up. So it works there where x is what than 5? X is greater than 5. Okay, so we're going to say that, or really how I can just put it is, instead of saying, oh, x is greater than 5, it looks weird like that. What you can just say is x is less than 1 or x is greater than 5, then tell them, but x must not be equal to -1. And that would be your answer for that question. So with graph interpretation, you just have to be very careful to make sure you are looking at the graph and looking at it thoroughly to make sure that you did get everything that it's working for and everything that it's not working for. Okay, so that is 9.3. We finally move on to the next question. Okay, 9.4 says, for which values of t will the graph of p of x is equal to f of x plus t have two distinct positive roots and one negative root? So this one, it's still graph interpretation, but it's more like graph manipulation, okay? Because you're going to have to manipulate this graph, move it with drawings and stuff to see how you can achieve these roots they're asking for. Please note that they said for which values of t, okay, so solving for t this time, will the graph of p of x is equal to f of x plus t. So this is a new graph when we're adding t, have two distinct positive roots and one negative root. So you know you can't use delta here because we're working with a cubic function, one. And secondly, they're asking for very specific roots. When they start asking for things like positive and negative roots, you can't really use delta for that. Delta doesn't manipulate roots to that extent. So we need our graph. Let me go ahead and get our graph. And when we have our graph, they asked for, and I'm glad, not that it wouldn't have worked if it was negative, but I'm glad it is positive because it's just simpler when it's positive, okay? So I'm glad that t is positive. So f of x plus t will it have two distinct positive roots and one negative root. Let's look at the roots that it has right now. Right now, it has only two roots, right? One is negative and one is positive. We needed to have three roots, but specifically three roots where two are positive, one is negative. So I'm going to draw an outline of this graph so I can properly move it up or down just so that we can see what is happening in this graph. Okay, so this is the outline that I drew, and we are going to go ahead and move this. So because we have plus t, t can just be anything. We're just going to think about what it should be. Are we moving it up? Are we moving it down? Let's go ahead and try moving it down. If you took this graph, you moved it down, look at what happens. See the issue here? No roots here, and you only have one root. So clearly moving it down is not an option. We need to move it up. So moving it back to its original position, if you move it up, what happens? Okay, so let's just move it up just by a little bit. So if it went just beyond it being at the x-axis, do you see now that what you would have is you have one root there, another, and another. Three roots. But the thing is we want two positive roots, one negative. Now you have two negative roots, two negative x-intercepts, and one positive. That's not what we want. So you would have to keep moving it up to see how that works. If you keep moving it up, let's say we move it to here. And this is a very important point because you see that after moving it from this point, right, where it is touching the x and the y-axis at the same time, if you move it beyond this, that's when you actually see one negative root and there's a positive and a positive root. So this is a very important key point here. What happened here? So you see that if we move it till here, right, if you just move it a little beyond this, that's when you start getting the roots you're looking for. So how must we move it for it to look like that? Think about this. We moved it to a point where the y and the x-intercept are both at 0. Before, the y-intercept was at what? We already knew that number. It was at -5, and you moved it to the point where the y-intercept was at 0. So how far up did you move it? How many units up did you move it? If this is -5, you must have moved it 5 units up so that it can land here. Okay, so that's a key point we're going to put there. Then I'm just going to copy this graph and actually put the proper one that we're supposed to have. Let's just change the color of it. We can change it to blue. Okay, so this is still our graph, still moving it. So now when you move it up, yes, now we finally have one negative root and two positive roots. So now we know that if you move it anything more than 5 units, you're going to have your negative root and your two positive roots. That's great. But must we just move it more than 5 units and just let it continue moving up more than 5? You can just continue shooting up more than 5 units. No, we can't do that because at some point, if you do that, it's only going to have, because that's going to extend down, it's only going to have one root and then nothing there. So it means that now you need to tell it where to stop. That's what we're really doing with this graph. So we know we need to move it up more than 5 units, but how far up? Okay, and let's just see. Let's move the graph and see what happens there. Okay, so for this, I created a green graph. So if I just kept moving it up and up and up and up, what happens? Still has the roots I'm looking for, negative and positive and positive, negative and positive and positive, until I get here. What happens when I get here is that I don't have 3 roots anymore. I have 2 roots. Do you see the key things we need to look at? We should not move it past this point. But how do we know how high that is? Because I know I must move it more than 5 units, but how much should I not move it past? Well, you can find out that by looking at what the y value was here, right? And when you moved it up to that green point, what is that y value now? That y value will be 0. So you just have to find out what exactly this y value is, and you tell them that you should not move it anything more than that amount of units. Because if it, for example, was like -9, right? Then it means that if you move it 9 units up, then the graph is going to sit like the green graph, and you shouldn't move it anything more than that. So another thing is we need to find that. So this was the local minimum. Let's find the y value of the local minimum. So now it makes sense that they asked us for the x value of that local minimum. We have the x value, we'll find the y value. So let's substitute 3 into that equation. So I'll put that calculation down. We'll say f of 3 is equal to 3 to the power of 3 minus 3 times 3 all squared minus 9 times 3 minus 5. And let's find that answer. And that number is much further than I thought it would be. It's f of 3 is actually equal to -32. So now we know that number. Okay, so that calculation, I'll leave it down there because it's going to be very helpful. So now I know that number there is -32. So we should move it more than 5 units. Anything more than 5 units would give you a negative root and 2 positive roots, but nothing more than 32 units, because when you move it more than 32 units, when you move it 32 units exactly, you're going to only have 2 intercepts. And if you move it anything further than that, you only have 1 x-intercept. So how we would write the values of t is like this. T should be bigger than 5. It should be more than 5, but it must be less than 32. Move it anything more than 5 units, but nothing more than 32 units, and that's your answer. Okay, so that is the last question for question 9. Then we finally move on to question 10, which is our last question for calculus. And now we're on question 10. Question 10 says, EHGF is a rectangle. Now we have HE, okay, produced x squared centimeters to n. Okay, so HE is produced x squared centimeters to n. Okay, so that is being produced to n. Then they tell us that EH is produced x squared centimeters to p. So EH is produced x squared centimeters to p. Then they tell us that NF produced intersects PG at M. Okay, so those two get produced and they intersect at M. Then to form an isosceles triangle, MNP. So this is an isosceles triangle. So they're already telling us that this and this, those are equal. Okay, with, of course, they say it's NM being equal to PM or MP. D right there lies on NP, where MD is perpendicular to NP. So we have perpendicular. And then they tell us that NP, that is 4 units. And MD is 3 centimeters. Okay, they're all in centimeters. So MD is 3 centimeters. Okay. 10.1, you need to show that the area of EFGH is given by A of x is equal to 6x squared minus 3x cubed. Okay, so let's work with that. Let's see what we're going to get there. Okay, so let's just establish a few things. First of all, they made it very clear this is a rectangle. They said the rectangle. So we can consider all the properties of a rectangle on this. Okay. Regardless, they told us that these two lines, that and that, are equal. So that line and that line. So we have an isosceles triangle, and that's x squared, that's x squared. This is a rectangle, and we can see this is perpendicular. So this is 4 units. So already you can see that these two triangles are literally the exact same triangles. This one is just flipped around. So they're basically, those two triangles are congruent. Okay, so those are congruent triangles, and we can actually see them because you see you have a side being equal, we have a common side and an equal angle. They're both 90 degrees, so they're congruent. But this is not Euclid, so we don't have to give them reasons. We just have to conclude certain things. Okay, let's actually focus on, because I don't like to find things. I know I'm just analyzing a lot too much here. It's just because the shape looks intimidating, that's really all. But let's actually focus on what we would do to find what they told us to find. They said find the area of that rectangle. Naturally, to find the area of a rectangle, you just take the length and you multiply by the breadth. So if we're looking at that, they already call that B. So we need to take the length, which is EH, and we need to multiply by the breadth, which is EF. And now I don't have to go searching for random things. I just have to focus on what I need to find. I need to find EH and EF. So we'll look at that. How do we find EH? Okay, that one seems quite simple to find. They told you this entire thing is 4 units. From here to here is x squared. From here to here is x squared. You see the remaining part is EH. So to find EH, you would just take the entire 4 units and you minus it by this little part, the x squared, and you minus it by that other part, the x squared, and you'll be left with your EH. So EH in terms of x is 4 minus, see, negative x squared minus x squared is negative 2x squared. Okay, so we have EH, check. Now we just need to find EF. Let's look at this. How can we find EF? Okay, since this is part of a rectangle, a rectangle has certain properties. So let's actually consider the properties of that rectangle. First of all, a rectangle has 2 pairs of opposite sides being parallel. So that's parallel to that. And this is parallel to this. Sorry, I should give that a different type of marking for parallel. Okay, how does that actually help us? The goal is to find EF, so everything I should use should be to find EF. Let me look at this for a while. Okay, so when I looked at this for a while, at first, I was trying to consider, using like Pythagoras or something like that. But that's not really possible because unfortunately, like if I try to use Pythagoras on this, I need to have NF. Then I went on a whole spree of looking for NF and I did not find NF. So that's clearly not working. So what I'm going to go towards, because we have parallel lines, is I'm going to try and see, because I also noticed, remember that they told us that MD, right, is 3 units. Let's keep that in mind. They gave us that for a reason. There's no way they just put it there so that we can't use it. So because of that, I thought maybe we can use the proportionality theorem. If you tilt your head this way, right, you see this is a big triangle that you have. Because that's a triangle that you have, you can use the proportionality theorem. Now, here's the thing about this line MD. It is a vertical line. We know it's a vertical line because it is perpendicular to our base, right? And our base is part of a line with a rectangle. A rectangle is made up of a vertical and a horizontal line. So this is a horizontal line, so this is vertical. Because it's vertical and these ones are vertical, they're all parallel. So if you tilt your head, let me just actually put that in black. So parallel, parallel, right? If you tilt your head and you look at the triangle NMD, do you see that you can use the proportionality? Well, it's not proportionality theorem I'm seeing here, because if it was proportionality, I would have to kind of like use this, maybe NF and NM, right? And then NE and ND. And that's not really possible because, yeah, sure, I can find NM because of Pythagoras, but I can't really find NF. That was the first headache in the first place. So it's not proportionality. Instead, you can try and use similarity. Look at these two triangles. Look at NEF and look at NDM. Those two triangles will be similar. You would know this from the similarity proof. I also have a video on that. Okay, so I'm not going to have to prove anything. This is not Euclid. So what I'm going to say is, and I'm just going to write this down for the sake of it helping me find my proportions. I'm going to tell them that triangle NEF is similar to triangle NDM. Okay, and here's just a brief explanation for why they're similar. You have parallel lines, that's corresponding angles. Those two angles are equal. You have a common angle being equal, and by default the third angle in the triangles would be equal. So they're similar. And then we have, what we're going to do is we're going to use these proportions. Now I don't know how it's going to work. I just know I need FE. And so I'm just going to try my best to work through that, and hopefully it can help me find FE. So when you have similarity, when you have two triangles being similar, the sides are going to be in proportion in this way. So you see the side NE over ND. So you see NE over ND would be equal to the proportion will be equal to EF over DM. And that would be equal to NF over NM. Okay, and M. So I'm just going to fill in what we have, and hopefully we'll be able to find one for FE. We will definitely will be, because it's structured like that. So NE is x squared. So we're going to fill in. That's x squared. And D, what is ND? ND. Okay, so you see with ND, because this is a congruent, you see I showed you that these two triangles are congruent. You have an equal side, common side, and an equal angle, right? It would mean that this little part ND is 2 units, and that one is also 2 units, cut in half since it's a total of 4 units. So we have that. We have ND, it's 2 units, 2. Don't need reasons, it's not Euclid. EF. Now, where's EF? EF is this. What is what we're looking for? It's fine if it's empty, no problem, because we're looking for that. Over DM. DM is 3. Yay. So this is actually looking very good. I would have gone ahead and go and find these, but I see I don't even need them anymore. I just need these two. I'm going to work with that. Okay. So I'm just going to erase that. Don't really need that. This is, of course, because of similar triangles. Okay, the reason I say I don't need that, because you see that here, the only thing missing, the only side missing is EF. Everything has a value. This is x squared, but it's still in terms of x. So to find EF, we're dividing by 3. So to get rid of this 3 so that EF is alone, you'd multiply both sides by 3. And then it would mean that you're left with EF, because the 3's would cancel. And here you'll be left with, you have 3 and x squared over 2. You can write that as 3 over 2 x squared. That's EF. Finally, we found EF. So there we have our 2 sides that we needed, and we can go ahead and use this now. So again, we're saying that the area is equal to EH, which we know is that, times EF, which we know is that. Okay, because this is one term, I'll write it first. That's x squared being multiplied by something that has 2 terms. So you need to use brackets so that it can multiply into both terms. So that's 4 minus 2x squared. Okay. Then we have A is equal to, we're going to multiply. So if you distribute in 3 over 2, maybe I should show you what this is going to do, times 4. What actually happens is when things are common, they cancel diagonally and also top and bottom like that. So diagonally, do you see that 2 is common? You're saying 2 divided by 2 is 1. 4 divided by 2 is 2. So all that's left is 3 times 2, which gives you 6, right? So in the numbers, that all that's left is 6. Then you still have x squared. Then if you multiply that as well, let's see what happens. So 3 over 2, I'm working on the numbers first, times negative 2. You see that diagonally 2 would cancel. 2 divided by 2 is 1. 2 divided by 2 is 1. So this is a negative 1. 3 times negative 1 is negative 3. And then of course there are x's. So x squared times x to the power of 2 as well is x to the power of 4. And there we go. That's a of x. I've been calling it a of x. And we finally found the value of a of x. Okay, so that's that. 4 marks. Moving on to the last question of question 10. Okay, and then the last question is calculate the maximum area of rectangle EFGH. Okay, so this is the area of it. To find the maximum area, you first have to find the value of x for which this area will be a maximum. Okay, so we're going to take our function, and to find out its maximum x value, you're going to derive the function, basically finding the gradient, and then you're finding where the gradient is equal to 0, because at stationary points, this is where this graph is, neither increasing nor decreasing. Those are the points that are sitting still on the curve. So on most curves that you see, these would be really key points to find whether this is the maximum or the minimum. Okay, so we're going to find the value of x for which this is going to be a maximum. To do that, you're finding the gradient of the function, and you're specifically finding where the gradient is equal to 0. So we're going to say a prime of x is equal to, that will give you, so multiply, we get 12x. Then negative 3 times 4 is negative 12. And we have x to the power of 4 minus 1, which is 3. Okay, so this is our function derived. Then you're going to set it equal to 0 so that you can find that maximum or minimum point. Okay, those turning points, the stationary points, is equal to, we have 12x minus 12x cubed. I can take that over, no, not really. Since they both have 12 and x, just take out 12x as a common factor. Then you're left with here, if you divide that by that, you get 1. If you divide this by that, you get negative x squared. Okay, so this is what we have. So we can say this can be factorized further. You can use difference of two squares if you want. It's not necessary. So I'll just say 0 is equal to 12x, or 1 minus x squared is equal to 0, right? Because they're being multiplied. If you have something times something and they give you 0, it's either that this one is equal to 0 or that one is equal to 0. So divide both sides by 12, and then you see that here 12 cancels. 0 divided by 12 is 0, so it means x is equal to 0. That's one solution for x. And here I'm just going to do this simple way, not the difference of two squares. So take negative x over, it becomes x squared. Square root both sides, but because this is an equation, you must say plus minus. So x is either equal to positive 1 or x is equal to negative 1. Okay, how do we know which one is our maximum? Well, this is not, a normal function that we're used to seeing. It's not a parabola or cubic function. So all you can do is really just substitute. We're going to substitute and see which one works. And I try a of 0 into our function of a of x. What do we get? I get 0. So that's just 0. If you try a of 1, a of 1 and a of negative 1, they're going to be the same thing. See, this is the reason why. Because here the x gets squared. So even if it was negative, it will become positive. And here the x gets raised to the power of 4. So even if it was also negative, it would be positive. So these ones will give you the same answer. So it doesn't matter actually. You can take either one. So let's try a of 1. If you substitute 1 into that, let's see what we get. We get 3. Okay, 3 centimeters squared, of course, because it's area. If you change it to, this is what I was saying, if you substitute negative 1, you're going to get the same thing. You see that a of negative 1 is also 3 because of that squared and that 4. So as you can see, the maximum out of that, the highest area that we can get from that shape would be the 3. So we can tell them that the maximum area, okay, is 3 centimeters squared, since they told us all of that was in centimeters. So that is the end of question 10, and that is it for calculus. We only have probability left for paper 1. So that is it for this video, and I will see you in the next video.